This is the first video in the lecture series Data Analysis and Machine Learning. Hi, my name is Eik van Vuren, and today I'm going to look at a very interesting part of data science, and that is machine learning. That's a part of data science that has been recently developed. That means that today what I'm going to do is that I'm going to look at an introduction to machine learning. More particular, what I'm going to do is I'm going to look at an introduction for econometricians with respect to machine learning. Well, the reason why I'm going to do that has nothing to do with machine learning itself, but it has all to do with actually US students, because of the fact that US students, well, this is a master in econometrics, and that means that most of you must have already had some of data science before. In particular, you must have had a lot of econometrics before. Most of you already went to do a bachelor in econometrics, and that means that you do already know quite a lot about data science. That means that, in my opinion, it would be not such a good idea to say, like, now that we are going to look at machine learning, another, say, part of data science, then I'm going to say, like, well, let's forget about everything that you have done so far and let's start completely anew with a new tool or a new part of data science, which is machine learning. Instead, what I'm going to do today is that I'm going to give you a special introduction for econometricians. That means that I'm going to focus on what are actually the differences and actually what are the things which are similar between econometrics on the one hand and machine learning on the other hand. That means that what I'm going to do today is that first of all I'm going to give you an overview of econometrics. You know already a lot about that, of course, and then I'm going to go on with machine learning. Then, after that, I'm going to focus especially on the differences between machine learning on the one hand and econometrics on the other hand. And then finally I'm going to realize that even though there are differences between econometrics on the one hand and machine learning on the other hand, we can actually use machine learning in econometrics to in fact improve econometrics. Well, before I'm going to do that, I would like to say that there are actually two different kinds of data analysis. That is something that I already said so far in the introduction. There is, on the one hand, you could say statistical or econometric analysis. I'm going to say much more about that on the next slide. And in addition to that, there is machine learning. Now I'm going to say also a lot more about machine learning, but before I'm going to do that, I would like to give you I would say a short definition of machine learning. It's always nice to have a short, I would say, one sentence definition of a particular topic, in this case machine learning. This is not something that you have to learn by heart, of course, but if I'm going to give you a definition of machine learning, then I would say that machine learning can roughly be described as a set of algorithms that help to understand the data, usually by making predictions. There are a couple of things which are really important with respect to this particular definition. First of all, we have the algorithms. The algorithms are very, very important in machine learning, which is actually different from econometrics, as we will see on the next slide. And these algorithms actually do have an important goal. They have a goal, in this case, to help to understand the data. And as we will see later on, is that, well, it's not always the case that we are going to use machine learning in order to, well, to make predictions. In many situations, we are going to predict in machine learning. But let me now go on with, say, another important part of statistical analysis, and that is econometrics. Well, what we can say is that also here I would like to give you a particular definition, and here the definition is that statistical or econometric analysis is a science that uses stochastic models in order to describe the data and use that data to estimate parameters of that model. Also here there are a couple of things which are really important. First of all, we are going to see that econometric and statistical analysis tries to use models. It's not algorithms that are here important, but they are models which are important and they are used in order to describe the data. And the ultimate goal, in a sense, is that we would like to estimate parameters of that particular model. There are parts of the, say, model that we are ignorant about. We have to make assumptions with respect to the model. However, there are some parts that we will like to be ignorant about. These are called the parameters, and we're going to use the data in order to get information about those parameters. Now, you immediately see that actually I have not made a different definition from econometrics and statistics, which actually implies that you might get the idea that econometrics and statistics, it's in sense the same. Well, that's partly true, but we should take into account that even though statistics and econometrics are more or less the same, we should realize that econometrics is in that sense different, and also looking at a course in econometrics usually is different from a course in statistics because of the fact that there is a different focus. In econometric analysis, the focus is usually on so-called causal relationships in data models that are realistic for social sciences. Well, I'm pretty sure that you already know a lot about this, but let me give you an overview with respect to that. And the standard model that we usually then look at is a so-called causal outcome model, sometimes also called the Rubin causal outcome model. In order to introduce that particular model, let us actually look at the variables. We have now a variable that we are going to denote by x, and that is going to be observed. And what we're going to have is that we are going to have, say, n observations of that particular variable x, and we're going to denote them by xi. And I'm going to assume here, just to make it as simple as possible, that they are so-called IID, independently and identically distributed, and they're an IID sequence of dummy variables. And well, let's make it as simple as possible. Xi is equal to 1 in the case that I belongs to a particular treatment group, and Xi is equal to 0 in the case that it actually belongs to a particular control group. We usually call this treatment groups because of the fact that in medical sciences, usually we are going to talk about a medical treatment. People are going to receive some treatment. However, in economics, we could also think of many other examples. But in addition to that, we also have say outcome variable, and that outcome variable is here denoted by y. And also here we're going to assume that we have n observations with respect to the outcome variable, so we're going to denote it by yi, and also here we are going to denote it I is, well, from 1 to n. And it's going to be an observed outcome variable, and we're going to have, say, yi is equal to either yi1 in the case that xi is equal to 1, and yi is equal to yi0 in the case that xi is equal to 0. So that implies that what we do actually observe is xi, and we observe yi. We can immediately think about examples here, and the most simple example that we can actually think about is, of course, a medical example. That means that xi means that you're going to get some kind of treatment. Well, it could be meaning that you're going to be prescribed some kind of medicine, and then in addition to that, we are going to have that yi is in fact your health status. So we're going to give these medicines to individuals that have a particular kind of illness, and then after a while we're going to follow them and we're going to look at their health status. That could be either whether they're still alive or not, if we have a very serious disease, or it could be the fact that these individuals are already, well, they are already healthy again, they don't have the symptoms anymore, or they at least have particular kinds of symptoms. So therefore yi is in this case the health status of the particular individual, and xi is the treatment of that particular individual. However, we should immediately realize that there is a problem over here, and the problem is that we only observe only one of the two outcomes that we have. We only either observe yi1 in the case that, of course, xi is equal to 1, but then we are completely ignorant about yi0. And on the other hand, it is the case that at the moment that we actually are going to observe yi0, well, that is of course the case in the case that somebody is going to have an xi equal to 0, but then we are completely ignorant about yi1. Take that into account with respect to the medical example that we have looked at so far. The moment that we are going to look at a particular individual that has received, say, the medicine, well, then of course we do know what the health status of that particular individual is after a while. If he would have taken the medicine, because of the fact that this particular individual took the medicine, so his health status is actually equal to the health status in the case that he would have taken the medicine. However, we have no idea what the health status of that particular individual would have been in the case that that particular individual would actually not have been given the medicine. So we do actually now know yi1, but we have no idea about yi0. On the other hand, of course, if we are going to look at an individual that didn't receive the medicine, well, then we do actually know yi0 because of the fact that that is then the health status in the case that you did not receive a particular medicine. But we have no idea what the health status would have been, the health outcome of that particular individual would have been, in the case that that particular individual would actually have taken the particular, say, medicine. So therefore we have a problem over here. Well, before we're going to talk about whether this problem is going to be actually problematic with respect to estimation, the first question that we always have to ask in econometric analysis is what are we actually interested in? Well, generally we're interested in whether the treatment must have had some impact. So therefore we can look at things that actually give us an indication whether the treatment actually gives us some kind of impact. And well, even though we can look at many different things, one thing that we can look at is the so-called average treatment effect. What is the average treatment effect? Well, it is actually nothing else as the mean outcome of y1 minus the mean outcome of y0. Well, I would say in words, the average treatment effect is actually nothing else as what we would have seen with respect to a particular population if everybody would have been treated. So the average outcome in the case that everybody would have been treated minus the average outcome that we would have had in the case that nobody would have been treated. That's the average treatment effect. It's of course an interesting thing to look at because of the fact that, for example, if this average treatment effect would have been equal to 0, well then actually the treatment, maybe the medical treatment, would not have had any impact, of course. So therefore the question that we are going to ask ourselves is first of all whether we can actually estimate this. But before we actually do that in econometrics, we always start with something else, and that's the problem of identification. Identification actually says nothing else as that we first would like to investigate whether it's actually possible based on the data, but the data are informable enough in order to give us the opportunity to actually estimate it. Well, that actually is nothing else as that we are going to ask ourselves the question, suppose that we know everything about the data. That means, in the case that we know, in fact, the data distribution, can we then actually know what the real values are? Well, that means, of course, that the average treatment effect in this case is identified. In the case that the two terms that we have in the average treatment effect, well, the mean outcome of y1 and the mean outcome of y0, they must be then identified. So let's first of all look at the mean outcome of y1. Well, based on a very famous rule, that's the law of iterated expectation, we can actually rewrite the mean of y1 a little bit. We can rewrite in such a way that we are going to get, first of all, the mean of y1 conditional on x equal to 1, multiplied by the probability that x is equal to 1, plus the mean of y1 conditional on x equal to 0, multiplied, of course, that the probability that x is equal to 0, but that's of course nothing else as 1 minus the probability that x is equal to 1. And now, of course, the question arises whether the right-hand side that we have over here is going to be identified. Well, that's the same as saying that we must have that if we know the data distribution, then we should be able to immediately know all the things that we have over there in that particular equation. Well, what we can do is that we can first of all look at the very first part that we have over here. That's the mean of y1 conditional on x equal to 1. What is that? Well, that's actually nothing else as the average outcome of, say, the treated situation for those individuals that are treated. In our medical example, this is the average outcome, say, of the health status when you have taken the medicine among those individuals that have taken the medicine. Well, that's of course truly identified because of the fact that we do of course know the health outcome when you're going to take the medicine for those individuals that actually took the medicine. So therefore the very first part is definitely identified. What about the second thing that we have in our analysis, the probability that x is equal to 1? Well, that is something that is definitely observed, or that is at least known at the moment that we know the data distribution. And the reason behind that is because of the fact that x is observed. So therefore also the probability that x is equal to 1 is identified. That means of course also that the 1 minus the probability that x is equal to 1 is of course also identified. Then finally we can then look at the final term that we have, namely the mean of y1 conditional on x is equal to 0. Well, that part is definitely not identified, and the reason behind that is simply because of the fact that we have no idea what actually the outcome in the case of taking the medicine would have been for those individuals that didn't take the medicine. More in general, of course, we actually have no idea what the outcome in the case of treatment would have been among those individuals that have not taken the treatment. So that implies, of course, that the mean of y1 conditional x equal to 0 is not identified, and that means, of course, also that the mean of y1 itself, the left-hand side, is not identified. Well, the same we can actually say with respect to the mean of y0. Also, that is actually not identified, and that means that we can, based on this, say that the average treatment effect is actually not identified. That means that we can actually not estimate it. Even if we have perfect data, then the average treatment effect can actually not be estimated so far. So therefore, the problem is that we could actually not go on with estimation. So the question then of course arises, what could we do in this particular case? Well, as econometricians we have two opportunities in this particular situation. Either we could do nothing and we could just say like, well, we cannot estimate the average treatment effect. That's maybe a little bit disappointing. The other thing that we can do as econometricians is that we can say like, well, of course, the average treatment effect is not identified under this particular kind of model, but we can of course change the model a little bit, make additional assumptions in such a way that it becomes identified. Well, I'm going to do it here a little bit different than the standard way in econometrics. I'm going to first of all ask myself the question, what is actually identified in our case? Well, it's immediately clear that two things that are identified in our case are the mean outcome among those individuals that are treated and the mean outcome among those individuals who are not treated. Of course, since we do know the outcomes, we can actually look at their, say, outcomes among those individuals who are treated, and we can also look at the outcomes among those individuals who are not treated. So therefore, what we can ask ourselves the question is, might it be possible that the average treatment effect in some cases may be simply equal to the difference between the mean outcome among those individuals that are treated minus the mean outcome among those individuals that are not treated. It's immediately clear that the average treatment effect here that I have defined here is different from the one that we had before because of the fact that, of course, we now have the mean outcomes conditional on whether you're treated or not. Well, but we can immediately realize, of course, that the mean outcome of y conditional on x equal to 1, that's of course nothing else as the mean outcome of y1 conditional on x equal to 1. And with respect to the other one, we can realize that it's of course nothing else as the mean outcome of y0 conditional on x equal to 0. So we can actually write it like this. But then it becomes immediately clear then the question whether the right hand side over here could be equal to the left hand side, namely the average treatment effect, depends on whether y0 and y1 are uncorrelated with x. If they're uncorrelated with x, if the potential outcomes y0 and y1 are going to be uncorrelated with x, well then we actually have no problem. We can actually estimate the average treatment effect directly from the mean outcomes among the treated minus the mean outcomes among the non-treated. However, the problem that we have in social sciences is that this is actually almost never the case. And the reason behind that is because of the fact that we should realize that usually the x's are based on decisions that individuals have to make. If we go back to the example that we have looked at so far, then we should realize that our example was whether people had to take medicine or not. Well, if you let people freely choose to take medicine or not, then actually people are going to choose what is best for them. If they have the idea that for them it's very important to take the medicine because of the fact that that makes them healthy, then they will actually take the medicine. And for people that actually have the idea that it's not so important for them, maybe because of the fact that they are not so ill, or maybe because of the fact that they already know that they're going to die anyways, they actually will not take the medicine. And that makes it impossible to assume that X is going to be uncorrelated with the potential outcomes. However, there is a way out here. And that's the way out that is actually always used in medical sciences. And that's the way out of random control trials. What we can do, of course, is that we can try to, instead of having the individuals to make decisions about X, we can actually make decisions about X. What we can do in a random control trial is randomly give people medicines and other individuals not. And then we know for sure that because of the fact that we do this completely randomly, it's going to be uncorrelated with anything, even independent with anything, including, of course, y0 and y1. Now, in medical sciences, we should realize that that's relatively simple, and it's actually also the only way in which you can actually do science in medical sciences. In social sciences, it's much more difficult, and that's the reason why we actually don't do so much of random control trials in social sciences. And the reason why we don't do that, there are many of them. They're ethical, financial, and there are also general equilibrium problems with respect to that. I'm not going to talk too much about that today because of the fact that then I can fill actually the whole lecture off today with respect to that. So therefore, instead, I'm going to ask myself the question, what do actually econometricians do instead? Well, econometricians typically use a combination of two methods in order to deal with these problems. The first possibility is to make the control and treatment group as comparable as possible. That we usually do by control variables and regression. Or we try to use random variation that naturally arises from the data distribution, and that's usually related to natural experiments or IV and regression. And then the estimation is usually based on the so-called analogy principle. If we can write our estimates, by the way, are nothing else as the things that you would like to estimate, such as, for example, the average treatment effect, we can write the estimates as the expectation of the data, then we can use the sample average to estimate that. And then the final thing that we're going to do is that we're going to do so-called statistical inference. Statistical inference is important to understand the quality of our estimators. Of course, at the moment that we do have estimators, we also would like to know whether these estimators make some sense, whether their quality is high or not that high. And for that we have two different kinds of, I would say, quality indicators. And these are either consistency and their precision. Consistency means nothing else as that if we actually have many observations and then limit indefinitely or infinitely many observations, then at that moment in time, consistency requires that actually our estimators are going to converge to the things that we want to estimate, our estimate. That is what consistency actually says. Precision is another thing. We should realize that typically we do not have infinitely large data sets, so that means that we always have finite data sets. And that means that even if we have consistency, it is possible that we sometimes overestimate our, say, estimate. We are going to be a little bit too high, or sometimes we are a little bit too low. And precision actually says how far we are in general off from the thing that we want to estimate. Now you should realize that consistency and precision, they are the two, I would say, quality indicators for statistical inference, but they do not have the same value. Actually, consistency is always more important than precision. That's to say that we always are going to, prefer a consistent estimator above an inconsistent one. And then the only thing that we are going to do next is then to look at precision. And the reason behind that is very easy to understand. Because what does actually consistency mean? Consistency, or inconsistency, better to say, means that we actually do not estimate the right thing. It means that we actually, even in the case that we have our perfect data set, we know everything about the data, then even in that case we're wrong, which means in sense that we are not estimating the correct thing. So that means that an estimator that is inconsistent but really precise means nothing else that we are very great in estimating the wrong thing. Well, that's of course not that good. So therefore, consistency always comes above precision. Now, an interesting detail is that there is relatively little attention to so-called model fit. How well does our model fit the observed data? Generally, actually, econometricians don't seem to be that much interested in that. True, of course, we usually report things like R-squareds in our linear regression analysis. We should take into account that R-squareds usually don't get that much of attention in linear regression analysis. And in addition to that, we will even see during this lecture series that the R-squared might not be the correct thing to use at the moment that you would like to look at model fit. And that is in sharp contrast to the other part of data science, namely machine learning. In machine learning, there is actually only one goal, and that is model fit. That also brings me back to machine learning being, of course, the main objective during this lecture series. Now, I have already talked a couple of times about machine learning so far, but we should realize that there are two types of machine learning. The first type of machine learning is so-called unsupervised machine learning, and there the main objective is to understand the data distribution and to see patterns in that distribution. We do already know as econometricians that the data distribution is very important. However, especially at the moment that we have a lot of data available, then it is usually very difficult to get information from the data distribution. And that is the main objective of unsupervised machine learning. Apart from unsupervised machine learning, you also have supervised machine learning, and there the main objective is to predict the outcome variable based on observed characteristics. Here, the focus during this lecture series is going to be completely on supervised machine learning. I'm almost nothing to say about unsupervised machine learning. I'm only going to look at supervised machine learning. And the reason why I'm going to do that is actually twofold. The first one is a very simple one, and that is that I simply do not have enough time to discuss both unsupervised and supervised machine learning. And therefore I've chosen to only look at supervised machine learning. But the second one is more important, and that is that you have to realize that at the moment that we're going to talk about machine learning, these days a lot of people talk about machine learning, even in the case that they do not know a lot about the things that we're going to talk about during this lecture series at all, then these people usually talk about supervised machine learning and not about unsupervised machine learning, which is more in the, I would say, academic arena. Another reason why I'm going to talk about supervised machine learning is because of the fact that I do think that it's much more important for you in your, say, future labor market. Now, there are many examples of supervised machine learning, and a very classical one is Facebook. I'm going to give you many more examples in the future, but a classical one is Facebook. I do not know whether still people do actually have Facebook accounts, but if you do have one, and at the moment that you even decide to upload pictures in Facebook, then you might already have noticed that the Facebook immediately draws, say, ellipses around faces that you have in your Facebook account. And the question, of course, arises, how does Facebook do that? Well, of course, Facebook doesn't have a lot of people employed that the whole day are going to draw ellipses around faces, but instead they use machine learning. What they do is that they're going to use pixel colors, but also the combination of pixel colors in order to use supervised machine learning and to predict whether there's a face in the picture or not. I would like to go on with another important part of this lecture of today, and that's the difference between econometrics on the one hand and machine learning on the other hand. Now, I can look at this very theoretically, but I do think it makes more sense to look at different kind of examples. In total, I'm going to have 2 of them, in which I'm going to notify when we are talking about econometrics and when we are talking about machine learning. And the first example is that one of the most important relationships in labor economics is the fact that higher educated tend to receive higher wages. Of course, it's true that if we are going to look at some individuals, then it may be possible that we're going to find an individual that is not that high educated at all, but still receives a very high wage. But in general, we can state, and this is also found by econometric research, that on average, individuals that have higher levels of education also receive higher wages. When wages are related to productivity, then this is relevant for economic welfare. We should realize that this is actually also found in econometric research, that wages are actually in fact related to productivity. And the relationship with economic welfare is very easily explained because of the fact that we should realize that at the moment that we have a higher level of productivity, then we can make the same kind of products by using less time, or we can make more products by actually working the same amount of time. So either way, we should realize that we're going to increase economic welfare. So therefore, an important econometric question is whether there is a causal relationship between wages on the one hand and education on the other hand. We do already know that econometricians are actually interested in, say, causal relationships. However, we should realize that even in the case that we do find that higher educated individuals tend to receive on average higher wages, then that doesn't mean that there is a causal relationship. It could be possible that even though we do find that on average higher educated individuals receive higher wages, that there may be other reasons, talents in fact, that tend to make that higher educated individuals also have higher levels of productivity and therefore higher wages. That's because of the fact that individuals that are higher educated could, for example, be smarter. They could be more intelligent or have other kind of talents in such a way that they are going to have, say, higher wages. And that implies that essentially this is not because of the fact that they're higher educated, but their talents make these individuals higher educated. They're going to help them at university, but they're also going to help them at the labor market by receiving higher wages. We should realize that this is of course also policy relevant. Investing in education is only welfare improving when there is a causal relationship. If there's no causal relationship whatsoever, we can of course invest a lot in education. It might make individuals higher educated, but they're not going to have a higher level of productivity. So therefore we should realize that for us as econometricians, it's really important to find these causal relationships. But now let's look at another situation. Now suppose that we have a firm and we are going to hire a new employee. We have to make a choice among many different candidates. This was actually until recently also the case for us as university. At the moment that we had an open position, then it was in many cases the case that we are going to receive many different candidates, maybe sometimes even more than 1,000 different candidates. And then of course the question arises, how are we going to make a choice among those candidates? Well, one thing we could do is that we could of course hire all the candidates that we have available, and then after, for example, a year, we are going to dismiss everybody apart from the most productive one. But that is of course not possible. That's very expensive and probably also illegal. So therefore we could do something else. What we could do is that we could look at, for example, things that are important for productivity, such as education. And in this case, it doesn't really matter whether there is a causal relationship at all or not. As long as education has a relationship with unobserved productivity characteristics, such as smartness in this case, one could select candidates based on their level of education. And it implies that in this case we are not doing anything else as trying to predict the wages, better to say the productivity of individuals, and that implies that now we're going to look at machine learning. I would like to go on with the second example, and that is an example with respect to houses data. I'm an econometrician, of course, and that implies that most of my research is in theoretical econometrics. However, with respect to the applications, I usually look at two different topics. That is, first of all, the labor market. Well, we have already seen an example with respect to the labor market at the previous slides, but I also look at housing data. So therefore, this example is going to be about houses data. And in order to introduce this example, suppose that you have been spidering for a long time a houses website like Funda in the Netherlands. Then I have to explain for those people that are not from the Netherlands, Funda, and without making any marketing for Funda, is actually one of the websites that you should look at the moment that you're looking for a house. And the reason behind that is because of the fact that at Funda all the houses for sale are actually listed, and that implies that you could of course use Funda in that moment that you would like to look for a house. However, what you could also do is that you could spider Funda, and that means that you're going to get data with respect to the houses that are for sale. That implies that you're going to get the house prices, actually better to say you're going to get the asking prices of the houses, and you're going to get all kinds of characteristics like the size of the house, the location of the house, as well as the number of rooms. Well, actually, most likely you get even more data with respect to that. You probably are going to get data about whether the house has a new kitchen, whether it has a garden, the size of the garden, but maybe even get information about the maintenance of the house. Well, suppose now that we are going to assume for this particular example that the only thing which is going to matter with respect to the house price is going to be the location in size in square feet. This is only going to be assumed for this particular example. In reality, of course, we do know that much more things are important. But for this example, we're going to assume that there are only two things which are really important, and that's the location and the size in square feet. Well, there is a famous saying in the Netherlands, and that is that at the moment that you're going to ask a real estate agent about what is important for the price of a house, what actually determines the price of the house, well then the real estate agent is going to say that there are three things which are important with respect to the price of the house. That's first of all location, it's second of all location, and the third important thing is also location. Well, that is only to say that location is very important for determining the price of the house. Well, that's of course true. Even at the moment that you're going to look here in Groningen, then you're going to see that say, locations like Eelde and Haren, as well as the city center of Groningen, they're much more expensive than some other areas in Groningen. So therefore, location is very important. But apart of location, you might expect that also the size in square feet is going to be important. That is to say that a very tiny house in the city center of Groningen might actually be less, have a lower price than, of course, a very large villa somewhat outside of the city center. We're going to assume that this relationship is going to be the correct relationship, but at the same time we're going to assume that the relationship is unknown to you. And then in addition to that, I'm going to suppose that the size in square feet is highly measured with error. Well, that used at least to be the case. I don't think that it's so much anymore, but it used to be the case that real estate agents, at the moment that they had to, measure the size in square feet, then they just walked into the apartments and they just looked at the apartment and said this house or this apartment has a size of, say, 800 square feet. However, at the moment that you're going to do it like that, then it's of course possible that the real size is not going to be equal to 800, but it might be, for example, equal to 900 or just 600 square feet. So therefore, we are going to assume that that's actually the case, that the size in square feet is going to be highly measured with error. That implies that, of course, the real size in square feet is going to be important for the house price, but that's not what you're going to observe. It's just the size in square feet which is measured with error. At the same time, we are going to assume that it is the case that a particular room always has the size of approximately 150 square feet. So that means that if we have a 3-bedroom apartment, that has a size of 450 square feet. Now we can do, of course, 2 different regressions. Well, in reality we can do many more regressions, but at least we're going to look here at 2 different regressions. And the first regression is a regression of price on location and size in square feet. And the second regression that we're going to have is price on location and the number of rooms. The question, of course, arises, which of the 2 are going to be preferred? Well, at the moment that we're going to look at the first regression, then we should take into account that that regression might actually not perform so well. And the reason behind that is because of the fact that we have that size in square feet is measured error, so therefore it suffers a lot from what we call in econometrics attenuation bias. That means in terms of t-values, that means that the t-values will generally be very low, and probably, the size in square feet might even be insignificant. And in addition to that, we're also going to see that the r-squared may be very low. On the other hand, at the moment we're going to look at the second regression, due to the assumption that there is a, fixed relationship between the number of rooms and the size in square feet, that second regression will actually perform much better. It will have a higher r-squared, and also the number of rooms will be highly significant. The question then, of course, arises, would it also be the best to use that particular regression in our analysis? Well, we should realize that that actually depends on the situation, whether you should actually use regression number 2, or maybe you should still use regression number 1. Well, now what we are going to do is that we're going to make this example a little richer. Suppose that the reason why you have been spidering this website was not because of the fact that you wanted to do research, but it was much more because of the fact that you wanted to make money. We would like to sell a house. And then we can look at 2 case studies. We can look at a situation in which, first of all, you are going to consider contracting a carpenter to build an additional room in your house. And the second case study is that you would like to know a good asking price. Well, let's first of all look at the first case study. At the moment that you're going to contract a carpenter to build an additional room in your house, that's going to be costly, of course, but it might, of course, be a good investment at the moment that the price of the house is going to increase by more than what you have to pay the carpenter. And therefore, one thing that you could do is to look at regression number 2, because of the fact that regression number 2 gives us a relationship between the price and number of rooms. And we're going to generally see that this relationship might actually be quite strong. However, at the same time, we as econometricians know that in this particular situation, this relationship is actually a spurious relationship. The reason why we do actually find that there is a relationship between the price and the number of rooms is not in this particular situation because of the fact that there is real causal relationship between the price and the number of rooms. The only reason why there is a relationship is because of the fact that we do of course know that prices are going to be only affected by the location and the size in square feet. It's not going to be related to the number of rooms, but because of the fact that there is a relationship between the size of a house and the number of rooms that it has, generally rooms or houses with more rooms also have a higher size in square feet, that implies that for this reason we are going to find that there is a strong relationship between the number of rooms and of course the house price. But it's a completely spurious relationship. Therefore, you might already have, had that idea. This case number 1 is all about econometrics. It's about causality. In this case, we would like to know whether there's really a relationship between, say, the house price and the number of rooms that we have. Well, we should realize that that of course implies that we should not look at regression number 2. Actually, we should even not look at regression number 1 because of the fact that that regression has attenuation bias. What we should do in this particular case is that we are going to use instrumental variable estimation. We first of all are going to run a regression of the size in square feet on the number of rooms. And then what we're going to do is that in a second stage we are not going to run a regression of price on location and size in square feet, but instead we are going to run a regression of price on location on, in fact, the predicted size in square feet based on the first regression that we had. That is IV estimation. But let's now look at the second case study that we have. We would like to know a good asking price for our house. Having a good asking price is of course important because of the fact that if we set the asking price too high, well then nobody will be actually interested in our house. At the same time, if we set the asking price too low, then of course a lot of people might be interested in the house, but they might not be willing to pay too much. So therefore it's very important to set the asking price correctly. And we do of course know that the asking price is highly related to the selling price. So therefore it might be interesting to know already the potential selling price. Well, take into account that in order to know the selling price, causality is not an issue here. The only thing we want to do is to predict well the, selling price. And for this case, it would be best to use regression number 2 because of the fact that that one is going to give us the best prediction. At least it's going to get us a much better prediction than regression number 1. So therefore, concluding, what we can say is that at the moment that causal relationships is our goal, then we should always use econometrics. However, in the case that prediction is our goal, then we should use supervised machine learning. I would like to go on with the next topic, and that's the topic of ethics and machine learning. Like in any other part of science, and even in everyday life, there are also ethical issues concerning machine learning. And it might even be possible to say that, maybe it's even more important in machine learning than in many other parts of science. And the reason behind that is because of the fact that many people are in fact afraid of artificial intelligence in general and machine learning in particular. And that's probably because of the fact that a lot of people have the idea that artificial intelligence takes over our everyday life, and it implies that people don't have to think anymore because of the fact that artificial intelligence is going to do that for us instead. That's also what is actually shown in many movies that have been broadcasted over the last couple of decades. In these movies you usually see a very futuristic, viewpoint, namely that, robots, or you could say artificial intelligence, is going to take over the world. You should realize that that's of course very futuristic and probably even not so serious, but we should also take into account that there are more serious issues related to ethics and machine learning. Well, actually, during this lecture series, we are going to ask you to come up with examples of that. But today I'm already going to give you two particular examples that I actually think are actually quite illustrative of showing that ethics are important in machine learning. First of all, there is of course the question, what are we allowed to take into account? So far, I have already talked a little bit about machine learning, and I said that what we would like to do in machine learning is to try to predict as good as possible, and for that we are going to use data. However, the question of course arises, can we use all the data that we have available in order to make the best prediction? Well, that is a difficult thing to say, but of course we can look at case studies, and a case study that is very interesting comes actually from the Dutch Tax Authority. The Dutch Tax Authority in the last 10 years has been, you could say, very enthusiastic of using data, you could say artificial intelligence, or maybe better to say machine learning, in order to try to predict whether somebody has committed fraud or not. That was especially concerning subsidies. And what the, Dutch Tax Authority did, among other things of course, but one of the things that the Dutch Tax Authority did was that they took ethnical background into account. Well, more in particular, what they took into account was the surnames of individuals. And it was actually shown at a particular moment in time that individuals that had particular kind of surnames that were not very, I would say, Dutch, then the likelihood that these individuals were predicted of, committing fraud, or actually were, in many cases even punished for committing fraud, was much higher than at the moment that an individual had another kind of surname that was a little bit more Dutch. Well, this was brought up in the media, and many people actually said that this was very racistic. And you could actually say that these people are in fact correct. And the reason behind that is because of the fact that in the Netherlands we have of course regulation. For example, in the Netherlands we have our constitution, and the first article of our constitution actually says that it is not allowed to take, say, things which are not important for a particular individual, to take them into account. And actually explicitly talks about ethnical background, that you're not allowed to take ethnical background into account at the moment that it doesn't actually count for that particular individual. And because of the fact that the Dutch Tax Authority, of course, is related to the government, that implies, of course, that the Dutch Tax Authority actually should obey our constitution. And that, of course, also implies that you can make a case for the fact that ethnical background cannot be taken into account at the moment that they're going to try to predict fraud. Well, another example is related to whether our sample is representative towards what we want to predict. And a very nice case study here is racial discrimination in face recognition technology. What you should take into account is that, what does face recognition technology do in general? Well, face recognition technology, and that's something that we're going to describe later on, general in machine learning, is that in order to do any prediction, or you could better say before that you're going to do any predictions, what you have to do is that you have to use what we usually call training data. That implies, in the case of face recognition, that you're going to give the computer many examples of pictures. These are going to be pictures in which you have a face, but also many pictures in which there's no face. And you're going to tell, of course, the computer in which pictures there is a face and in which pictures there is no face. That is for the, say, computer, in order to learn, in fact, to train itself in order to make better predictions. However, the problem that you have with respect to face recognition in this case is that by definition, of course, it is much easier to make then predictions for individuals that are from a majority than for individuals that are from a minority. That, for example, implies in the Netherlands that you might expect that it's much easier to make a prediction of whether a white face is in a particular, or somebody who is white and is going to be in a particular picture, than, for example, for somebody who is African American. Well, this was actually related to a case study that we had in the Netherlands during COVID. During COVID, actually, and I suppose that you still remember that, well, all these students had to make their exams at home. And many universities try to take into account that, well, students should not cheat, of course, as usual. And some universities, including the VU University of Amsterdam, they used software for these, anti-cheating software. And that meant that what the software actually was trying to check was whether the individual was all the time behind the computer. However, one particular student, and she was Afro-American, she said that she was all the time behind the computer, even though the software that actually said that she was not behind the computer. And she at least claimed that this was because of the fact that even though she was behind the computer, it was because of the fact that there was racial discrimination in face recognition. Simply the software did not recognize her face. Well, it's going to be very difficult to actually know whether she was correct or not, of course, but we should take into account that these issues actually do exist. In addition to that, we should take into account that all these issues are in fact related with how we use machine learning. It's not so much related to machine learning itself. It doesn't mean that since we have, say, ethical issues, we should not use artificial intelligence and machine learning anymore, but instead we should realize that it is all related how we use machine learning. If you, for example, are going to look to the very first case study that we have over here, we should realize that, well, at the moment that we are going to think about what we can actually use, what we can take into account, then we need laws for that. The law has to actually, well, decide for, in this case, the Dutch tax authority, whether they're allowed to use ethnical background or not. In addition to that, at the moment that we're going to look at racial discrimination in face recognition technology, well, then the only thing that you actually have to do is to omit these kind of problems, is oversample minority groups. Then at that moment in time, you will be better able to also, in fact, predict, say, those groups that are in minority. Another thing that we should take into account is the fact that all of these issues also play a role in everyday life. That is very well explained at the moment that we're going to look at our very first case study. What are we allowed to take into account? At the moment that we're going to look at the Dutch tax authority, then the question of course arises, what are the alternatives? Well, the alternative is of course very simple, and that is not using artificial intelligence. That is to say that we are going to go back to what the Dutch tax authority usually did, and that is that, well, individuals are going to check whether somebody committed fraud or not. But we should take into account that human beings are actually racist by themselves, unlike computers. Computers, of course, are not racist. The only problem is, of course, that they may take ethnical background into account because of the fact of the general case, which is not relevant for a particular case. But we should take into account that human beings are really racist. They actually will, at the moment that they're going to see somebody with a particular ethical background, they're going to make decisions based on not so much statistics, but they're going to do that purely based on their feelings. I would like now to go on with the final topic of today, and that is that we should realize that even though there is a big difference between econometrics on the one hand and machine learning on the other hand, that doesn't mean that we can use machine learning sometimes as a tool to improve our econometrics. And even though I'm going to look in the last lecture with respect to this lecture series, I'm going to look a little bit more into detail with respect to these kind of tools, I would like to give you today already a couple of examples in which machine learning can be interesting within econometrics. And the first example is related to instrumental variable estimation. I'm going to talk a lot more about that on the next slide, so therefore I'm going to skip that for the moment. I'm going to go on with the other examples. The second example is estimation of the treatment group if treatment would not have taken place, as for example in differences. This is an important topic. We do already know, actually from today as well, that what we would like to do in treatment analysis is that we would like to compare the treatment group, the outcome of the treatment group, with the outcome of the treatment group if treatment would not have taken place. In that particular situation, we're not going to look at the average treatment effect itself, but we're going to look at another statistic, which is the average treatment effect among the treated. Well, what we should realize is that, of course, the outcome of the treatment group, that is of course observed, but the outcome of the treatment group in the case that treatment would have not taken place, well, that is something which is not observed. That is something that we have to predict. Well, we should realize that that of course implies that that is actually more related to prediction than with respect to causality, with respect to econometrics. And it implies that machine learning can help us quite a lot in that respect. Another example is general predictions of lacking variables in data sets. We should realize that in many situations we might have variables which we could, for example, use as right-hand side variables. But it may be possible that in some cases some of the observations actually lack those variables. They lack outcomes, they lack values with respect to those variables. Well, we can of course decide not to use those variables, but instead what we could do as well is to use imputation. And imputation, well, that is used quite often in econometrics, but also here it has all to do in fact with prediction. Nothing with econometrics, but with prediction, and also here machine learning could be actually quite welcome. I promised you to say a little bit more about instrumental variable estimation, and as soon as we're going to talk about instrumental variable estimation, then these two regression equations should actually look very familiar to you. The first regression equation, well, which is usually called the outcome equation, has a yi at the left hand side, and the right hand side we have xi times beta 1 plus z1i beta 2 plus ui. Then in addition to that we also have a second regression equation which has xi at the left hand side, and the right hand side we have gamma 1 z1i plus gamma 2 z2i plus vi. It's immediately clear here that xi here plays a very special role because of the fact that in the first regression equation it is at the right hand side, and in the second regression equation it's at the left hand side. Well, in addition to that, we are also going to assume that u and v, well, they could be correlated with each other. Well, we should realize that that's always bad news, and the reason behind that is because of the fact that that implies that vi is both going to affect xi as well as ui. That's clear for xi of course because of the fact that vi is at the right hand side of the equation of xi, so therefore at the moment that I'm going to increase vi, then of course xi is going to increase with exactly the same amount. But because of the fact that we allow for correlation between u and v, that also implies that at the moment that I'm going to increase vi, then ui on average is going to change as well. But that of course implies that if vi both affects xi as well as ui, that implies of course as well that xi and ui are very likely to be correlated with each other as well. And that is always bad news, because that means that doing an ordinary squares regression of yi on xi and z1i will give us inconsistent and biased estimators of beta 1 and beta 2. However, we also know that there is a way out, and that is with respect to z2i. We have the following characteristics with respect to z2i, namely that xi and z2i are correlated. In this context, that means nothing else is that gamma 2 should not be equal to 0. In addition to that, we are going to assume that z2i and ui, they are going to be uncorrelated with each other. Well, then actually we could call z2i an instrument, and then at that moment in time we have a way out. What this actually means in words is that, of course, z2i is allowed to have an impact on yi. That's of course always the case, because of the fact that if z2 has an impact on xi and xi has an impact on yi, then z2i should also have an impact on yi. But this impact is not allowed to be directly through ui. Then in that particular situation we don't have a good instrument. And at the moment that we have a good instrument, so if 1 and 2 are going to be correct, well, then we do already know that we already have a very good estimation technique, and that is two-stage least squares. Two-stage least squares means that we are going to run, first of all, a regression of xi on z1i and z2i, and then what we're going to do is that we're going to predict the mean of xi conditional on z1i and z2i, and we're going to call this prediction xi hat. Take into account that this actually might be the worst, I would say, worst notation that we have in nowadays econometrics. And the reason behind that is because of the fact that what we usually do at the moment that we are going to use hats is that we indicate that we do not have an estimate, but instead we have an estimator. For example, if we would like to, in our first regression equation, if we would like to get an estimator of beta 1 of course is the estimate, then we are going to denote this estimator by beta 1 hat in order to indicate that's an estimator of beta 1. That implies that at the moment that we're going to write down xi hat, that implies that, well, most likely this is going to be estimator of xi. But that's of course not true. And the reason why it's not an estimator of xi is because of the fact that we don't have to estimate xi, because xi is actually observed. Why would we even try to estimate xi if it's observed? Because of the fact that the best estimator of xi is of course xi itself. Instead, what it actually is an estimator of the mean of xi conditional on z1i and z2i. And then in the second stage we are going to run a regression on yi on xi hat and z1i. Now this is called two-stage least squares, and we do know that two-stage least squares is consistent, but unfortunately it's also a biased estimator. So that means that for any finite data set we're going to have a bias. And this bias actually comes from the fact that we do not run a regression of yi on the mean of xi conditional on z1i and z2i and z1i. If we would have done that, if we would have been able to run a regression of yi on, say, the conditional mean of xi and z1i, then actually we would have had an unbiased estimator. But the problem is that we do not know what the mean of xi conditional z1 and z2 is. So therefore we actually predict it in the very first stage. But that means of course as well that the better we predict our mean, the lower is also going to be the bias. And now we should realize that of course prediction has nothing to do again with econometrics, but it has all to do in fact with, say, machine learning. And we should even take into account that in many situations z2i doesn't have to have a causal impact on the xi that we have at the left hand side. So there we can use, say, machine learning techniques. Well, later on we will see that lasso and ridge are going to be very helpful in this respect in order to be able to get a good prediction in this context.